It's the last talk of these 2 weeks, and Yuan will tell us about family Floer mirror space for local SYZ singularities.
Okay, thank you for the invitation, and thanks to the organizer for this wonderful conference. So today I want to talk about my very recent result. The title is Family Floer mirror space for local SYZ singularities. So the goal is to understand SYZ singularities by using the family flow theory. But at the beginning, I want to emphasize a sort of slogan: the dual singular vibration has a very elementary formula. So elementary means you don't need anything about family flow theory to understand that formula. The formula itself is elementary. Okay, so let's consider Lagrangian vibration with singularities. Yeah, let's say pi, and on some Kähler manifold, and denoted smooth part by pi 0. B0 is the smooth locus. But remember, we must place this pi 0 in X, not just in X0, because the holomorphic disk we consider are all sweeping in X. And we also need some assumptions. We require the Maslov indices of a holomorphic disk are all non-negative. And there are some nice sufficient conditions. So for example, special Lagrangians or graded Lagrangians. And on the other hand, we have another assumption, sort of a weak Armstrungness. For simplicity, we also consider a sufficient condition. So for example, we require the Lagrangian fibers are preserved by some anti-symplectic involution. For example, later on, we will focus on Gross's special Lagrangian, and then you just take complex conjugate for this involution. So due to the work of Solomon, the Maslov 0 terms in the Moore-Gardner equation will be canceled pairwise. So if you have some beta, this involution gives you another class in this relative homotopy group. So their contribution will cancel. But this never means the Maslov 0 counts vanish. They still contribute to both the work causing and the homological perturbations. Okay, so we want to study singular Lagrangian fibers, and we want to start them by studying 2 different types of holomorphic disk. So we have a sort of type 1 disk, which looks like the Wallichian cycle. So they are disks emanating from some singular fibers, but eventually bounded by a smooth fiber. This is a type 1 disk. And okay, so this is the reason why we must place the Lagrangian vibration in X, because we want to consider this holomorphic disks, and they can meet singular fibers. And on the other hand, we consider a different type of quantum corrections. So these are contributed by disk bounded by a singular fiber. Their boundary is already in a singular fiber. So you have 2 different types of disk. So alternatively, you can think the disk may meet the singular fibers at either interior point or boundary point. So you have 2 kind of disk. And we must deal with them in 2 different ways. So for the type 1 disk, we should focus more on the flow theoretic considerations. And this is basically done in my thesis. And on the other hand, for the type 2 disk, we should focus more on the non-Archimedean analytic or topological aspect. And this is what we want to discuss today. Okay, let's briefly review the mirror construction in my thesis. So you can associate to the previous pair, X and pi 0, a triple consisting of an analytic space, a phenoid torus vibration. I will explain this later, and a global function unique up to isomorphism of analytic space. So here lambda is a navical field. So it has a non-Archimedean valuation or norm. We also said lambda 0, lambda plus. And U lambda, the navical unital group, is sort of similar to U1. So said theoretically, the mirror space is not very interesting. You just take the union of all these first cohomology for these Lagrangian fibers. LQ is a fiber over Q with a coefficient in U lambda. So the Miller space as a set is just this. And a main point in my thesis is that on this set, we can further give some analytic space structure by considering the Maslow geodesic. And this analytic topology already contains part of the information of singularities because this disk can meet the singular fibers. Okay, now let me explain what is a phenoid torus vibration. It is simply a continuous map with respect to the analytic topology and the manifold topology on the base. So, and it is locally modeled on the so-called tropicalization map, like this. So you send a component to its evaluation. So I think it is the first introduced by Contrived Solomon, and it is further studied and is given this name by Nikashi, Xu, and Yu. And here continuous is really some strong condition in my opinion, because we use the analytic topology. So it's not like a manifold topology. It's a continuous with respect to analytic topology. And a brief picture of the mirror is as follows. So in the smooth locals, so you know, by Arnold-Liouville theorem, we have some integral affine structure on the base. So we choose the integral affine chart with some base point. So it's important to make a choice of the base point, and we allow the situation the base point is not in U, and the U is sufficiently small. Then we have a phenoid tropical chart, looks like this. So as a set, you just still take this union for Q in U, but we want to identify it with some analytic open subset in the non-Archimedean torus. And if you have two such chart, there's a transition map or gluing map between the two analytic open domains. And it is decided by some A-infinity homomorphism associated to some Lagrangian isotopy from LQ1 to LQ2. Here, Q1 and Q2 are the base point. But you can show it is actually the same for any A-infinity homomorphism obtained in this way. And this is carefully proved in my thesis. Okay, so this is a rough picture. And today, as I said before, we want to study singular fibers. So we aim to develop an analytic extension over B, not just over B0. So all possible continuous extension may be too much. So we want some additional condition. We add extra conditions to kind of control the extension. And based on our computations for the grossest special Lagrangian vibration, we propose to use the following condition: tropically continuous map. It is introduced by Chamber, Loyal, and Dorcas. And if you want a reference, you can see their famous paper in which they develop PQ forms on the Berkovich analytic space. So you can also do sort of a PQ forms similar to complex geometry. And the place is section 3.1.6. You can find the definition. And under this condition, the topological extension from B0 to BO can somehow control the analytic extension above. And I'm inspired by Gross's topological mu symmetry to think like this. Also, I'm inspired by Conservative Solomon's singular model in this paper, affine structure and the non-Archimedean analytic space, section 8. It has something similar. So roughly speaking, a tropically continuous map is locally in the following form. So here U is some analytic open subset, and F1, Fn are invertible analytic functions. So if you consider analytification of an algebraic variety, then you can, for example, just pick up the local coordinate. And here phi is just a continuous map for the Euclidean topology. So that's the definition of a tropically continuous map, roughly. So let's give a naive idea to explain why I need to introduce this notion. but I can be more specific soon. So very intuitively, let's imagine these valuations. These are just real numbers. You imagine they are action coordinates. And so they more or less correspond to symplectic area. But the symplectic area as a function on the smooth locus can usually extend to the singular locus. Yeah, if you compare this picture, you can just extend. This is just a symplectic area, something it's not so difficult. Anyway, we will focus on an example later. Okay, so next I want to explain why the conventional Morgan picture is not enough for the analytic topology. So it's been long expected that the mirror space should be the union of Morgan sets with singular fibers like this. Over the smooth locus, this roughly gives you the correct picture. And indeed, the Morgan set is very close to our first cohomology, which is a fiber, which is a dual fiber. But there are some slight difference. And in short, the set theoretic cosine condition is essentially straightforward by the homotopy invariance of Morgan set. And this is a property well known for the classic homotopy theory of infinite structures. However, I want to emphasize that for the analytic cosine condition, we must develop more powerful ideas and tools as in my thesis. And I can count at least 4 points below. So you need to study a uniform version of Grommer-Solomon's reverse isoperimetry inequalities for the non-Archimedean convergence issue. And you need to establish a minimal model version of Foucault's trig. And with non-trivial mass level zero this creates further difficulties. And you may wonder why we need to work with a minimal model. Very roughly, you want H1 rather than omega 1 for the dual fiber. And thirdly, you need to prove the transition maps are well defined. Otherwise, what the cocycle conditions mean is very ambiguous. And this requires the following UD homotopy. So you need to upgrade the classical homotopy to the UD homotopy for the infinite structures. The point is the analytic gluing needs some stronger sense of homotopy. The classical homotopy is not enough for this purpose. For example, the individual infinite maps satisfy the divisor axiom are not enough, and we want the homotopies. The homotopies between them also satisfy the divisor axiom in a very specific sense. And this requires lots of difficult homological algebra. And finally, we need to introduce a so-called category UD in my thesis. So in a word, the UD homotopy theory enables us to upgrade the classic Morgan idea to a higher and a more precise level so that we can match non-Archimedean additive convergent formal power series rather than just get set bijections. So that's I think this is a totally different story and is crucial for the analytic topology. By the way, the inclusion of Landau-Ginzburg superpotential will be also indispensable for our results later. Okay, so more interesting, let's consider the singular locus. The Morgan picture unfortunately fails. So you will see a Morgan set of a singular Lagrangian will be only a strict subset of the dual singular fiber. So what are dual singular fibers? Roughly, here the dual singular fibers extend our affinital torus vibration tropically continuously, as I said before.
May I ask a question?
Yeah, yes.
So this UD homotopy, should I think of this as just in quotes, adding some kind of continuity to the homotopies, or is that something?
Yeah,
what does UD mean?
Yes, thank you. Yes, thank you for the question. Yeah, I forget to mention here. UD means U stands for the unitality. So you know, infinite algebra have unitality issues, and the D stands for the divisor axiom. So you just add some actual conditions on the homotopy theory for infinite structures, and these actual properties will be useful to develop this analytical set condition.
Okay, thank you.
Yeah, thank you for the question. Okay, so yeah, so over the singular locals, the Morgan set is not the dual singular fiber. So of course, the Morgan picture gives you some good ideas, some inspiration, but unfortunately, it is eventually not the correct picture. Okay, so far we have studied the general theory, and next we want to go to a fundamental example, and I think this is also predicted by Grossi-Seibel program. So let's define X to be Cn minus this divisor, and equip with some standard symplectic form, and define Y to be an algebraic variety over the navical field, and defined by this equation. Okay, so our main theorem is simply saying that Y is SYZ mirror to X in the following sense. So now I want to make a precise definition. So we say an algebraic variety Y over the navical field is SYZ mirror to a complex manifold over the complex field if there exists a proper tropically continuous analytic vibration on some Zariski dense analytic open subdomain in Y. And there exists a Lagrangian vibration onto the same base manifold for the Kähler form, such as the following conditions hold. Okay, we have two vibrations over the same base, and we require this restrict to either a Lagrangian torus vibration or a phenol torus vibration over a common open subset, so that the two induced integral fine structure agree with each other. Okay, so I want to explain why we have two integral fine structure. Conservative Solverman proves that any phenol torus vibration also induces an integral fine structure on the base. So you have two integral fine structure, one from this phenol torus vibration and one from Lagrangian vibration. And we require they are the same. So in short, we can summarize this condition one as follows. So we want same smooth locus, same singular locus, same integral fine structure. And I think it is already a very non-trivial condition to achieve. The existence of a phenol torus vibration parallel to that of Lagrangian vibration should be also a non-trivial problem in non-Archimedean geometry. Second, there is an isomorphism of a phenol torus vibration between something abstract. This is a family Floer mirror vibration pi0 check, and something concrete F0. F0 is a restriction of this F. So you have something abstract and something concrete, and we require they are the same. So the rough picture looks like this. So you take some Lagrangian vibration with singularity, and we take its smooth part, but we still remember this holomorphic disk, which can meet the singular fibers. Then we run the family flow theory, and you get some abstract phenol torus vibration. And we want to sort of embed this family flow mirror space into some concrete algebraic variety, and we want to extend the phenol torus vibration in this algebraic variety. So this is a rough picture. And finally, we require this pre-image of the smooth locus is also Zariski dense. So probably this is a redundant condition, but it is useful for a folklore conjecture later. So let me keep it and to emphasize it. So in general, this Zariski dense analytic open subset depends on your omega and vice versa. This gives you a picture of a Kähler moduli versus complex moduli. For example, we can simply run this family flow business for the toric moment map. So what is your result? Your result is some analytic domain in the tropical, in the non-Archimedean torus, just given by the pre-image of the moment polytope. But you know, the moment polytope depends on your Kähler form. But if you take the Zariski closure, they are the same algebra variety, which is the whole torus. So we focus only on SYZ now, but hopefully we could achieve Abzois family flow functor to prove homology mirror symmetry in the future. Okay, here is a important remark. So you see this definition. The only place we use family flow is this condition 2, right? So if you allow me to remove the condition 2, still non-trivial to get condition 1, as I mentioned before, then you just need nothing about flow theory or Fukaya category stuff. There's nothing about modular space of a pseudo-homomorphic disk. So it may be very unmotivated without some flow theoretic considerations, but as we will see, the construction of this F itself is really something elementary. Okay, so let me, yeah.
So your point is currently why is the rigid identification of?
Yeah. You should think some analytification, and actually, it's better to use Berkovich analytification. But the difference between Berkovich theory and rigid geometry is very mild. Maybe I don't want to say too much about that. You need to do some analytification, and any algebra variety.
Analytic open domain, in what sense analytic?
Yeah, you have analytic topology and Zariski topology. So we are using analytic topology.
You're using, like, you're identifying Y with its close points, and then you equip it with this K topology. Is that like Y is an algebraic variety, which?
Yeah, Y is algebra variety, but you can analytification. You can take analytification.
So you take its rigid identification. And
Berkovich, and I think it's better to use Berkovich analytification. But so
it makes sense. I mean, the Berkovich identification will it fit into Y?
Yeah, Y.
Identification have a lot of points.
Yeah, but analytification for Y. So maybe we can talk about later. You have some algebra variety, you take analytification. Yeah, here you should say analytification. Here is an analytification.
That Y should be analytification. Okay.
This Y should be analytification.
Okay. And then you can say Berkovich analytification.
Yeah. Okay. Thank you for the question. Okay, so let's first talk about the A side. So we consider Gross's special Lagrangian. Yeah, the formula like this, which is well known, I think. The singular locus is given by some tropical hypersurface, which so that this minimum value attains at least twice. Yeah, in the dimension 3 case, this is given by this. So over the smooth locus, by the family flow theory, you can get some abstract affinitus vibration on this abstract set. And our Zariski dense analytic open domain in this, as you mentioned, analytification of this algebra variety is defined by setting the non-Archimedean norm of x1 is less than 1. So as you see, this is very explicit. And we will explain why we choose it later. And of course, you can change some convention, like you can exchange x0 and x1, or you can use another radius. It does not matter. Okay, now our major task is to find the construction of such an analytic embedding from the family flow mirror space to this concrete algebraic variety. So we want to find an embedding from something abstract to something concrete. And we want to find the dual singular vibration so that its smooth locus, its smooth part is the same as this affinoid, the family flow dual fibration, and through this embedding G. So let's first consider this G and then the embedding. By studying, word coursing and using family flow theory, we can finally show a simple identification. So which is not easy, but you can achieve this. So the family flow mirror space is simply the union of two analytic open subdomains in the non-Archimedean torus with so they depend on the action coordinate. So they rely on the symplectic form. And they correspond to the Clifford and the Chiganov tori, as you can imagine. And the gluing relation can be also written down explicitly. So you have two analytic open subdomains in the non-Archimedean tori, and you sort of glue them. And the gluing is given by some explicit formula. Under this identification, the analytic embedding is obtained by gluing some function, some map on T plus and some map on T minus, where H is this. So yeah, I think the expert will notice that this is something commonly used in other places. So the formula of this G is precisely due to gross hacking kill. But we further combine some non-Archimedean ideas from controversial Soberman. Yeah, so the reference is this birational geometry of cluster algebras, lemma 3.1. You can see something very similar, but it's over C. And also you can look at page 44 in this affine structures and non-Archimedean space. Yeah, you also have something similar. Because gross hacking here is over C, so let's discuss some ways of reduction from the navical field to the complex field. So the navical field is a residual field of, the complex field is a residual field of the navical field. So if an analytic space over the navical field is a generic fiber of a formal scheme over the navical ring, then the special fiber is a so-called analytic reduction, which is a variety over C, but in general, it is not unique. And also you can roughly think this non-Archimedean torus contains infinite copies of complex torus. So you can look at something called exploded tropicalization map due to same plane. And also you may study something called Maslow's dequantization. And this idea is studied by Mahakin and recently by Abzoy Ganachar Iritani Sheridan. Okay.
May I just make may I make a remark? I mean, this formula is actually not due to gross hacking kill. This is a kind of T=1 version of the wall crossing or kind of slab function crossing in the Annals paper with Mark.
Oh, okay.
I can explain later, but this is where it's coming from.
Oh, I'm sorry. I just find this formula in.
I'm sure it's there. Yeah, I'm just they might not have kind of given the background, but this is where it's coming from.
Okay. Yeah, I'm sorry about that.
No problem.
Thank you for pointing out. Okay, so yeah. Anyway, the navical field is good for the T duality idea. So you can more intrinsically you can think this T plus minus as subset in this abstract set, the union of flat connections. So if you have some point, you can identify it with some flat connection. So here is a flat connection, and the chi is the action coordinate for some basis of a fundamental group of Lagrangian fiber. So you do have some nice T duality picture. And the only place, okay, so here is a remark. The only place we use flow theory is this identification. I mean, it's not easy, but this is the only place you need the family flow theory. In fact, you just look at all this construction, this T plus minus the gluing relation, the embedding G, have nothing to do with the flow theory. You can just define them directly.
But I thought your point would be that they come, like they are what they are supposed to be because of the flow theory. I thought that would be the point. Is that wrong?
Sorry, I cannot hear clearly. So,
just like these abstract gluing, I thought kind of. Can you hear me now?
Yes.
So I thought, you know, you would say that they are what's written because of Floer theory, because that's what Floer theory requires. I thought that's what you would say.
Yeah. To show this identification, you need a flow theory. But you know, this gluing relation is something explicit. So you just have some explicit formula to make the gluing. So you can, for example, forget about this X0 check. You just work with T plus, T minus. That's also good enough. And you just need to use action coordinate. This is just about Arnold-Liouville theorem. So the counting, the flow theory counting tells you why we need to do this construction. But after you do this, after you find out this construction, you can forget about the flow theory. So that's my point. Does it make sense?
Yes.
Okay. So if we are content with the main theorem without the T-duality condition, so like this between the abstract family flow of vibration and this F0, then we can entirely exclude the flow theory in the business. Yeah, let me explain this more clearly later. Yeah, so you can replace this X0 check, replace it, and no flow theory anymore. Okay, so next I want to discuss this dual singular vibration. And I have to say, this is the most difficult part of the whole proof. And yeah, it takes me a lot of time. So we want to decompose it. So we obtain this dual singular vibration by decomposing it into a topological embedding, J, and an analytic tropically continuous map, capital F. So I will give a picture for this J later. So the diagram looks like this. So you do not define this F directly, but you first embed this base manifold into something higher dimensional Euclidean space, and then you can match, and then you can define this. So this decomposition exactly imitates a conservative model. And yeah, I would like to especially thank Tony Yu for his suggestion. So anyway, after a lot of trials.
May I ask, is this Y again, the analytification of what you wrote Y before?
Yeah. Yeah, here I think you should use, I'm sorry, yeah.
This should be YN or something, right?
Yeah, this is a curly Y, it should be a curly Y. Yeah.
I see, even curly.
Curly Y, yeah, curly Y, so that, yeah. Thank you for pointing this out. Yeah, this is the curly Y, not Y, because, okay, so after a lot of trials, we found the following pair by hand, and it finally works. So J is just embedding to Rn+1. It has some explicit elementary formula as follows. So you just take some minimum values, minimums, and here C it can be represented by some symplectic area of a holomorphic disk. Yeah, in the two-dimensional case, you can think about this disk, simpler area of this disk. But so you remember, this allows you to include the singular point. And F is defined by some other formula. So let me, it's a bit hard to explain, but let me compare this Z0 and F0. So we have two minimum for Z0, but they are separate. They are separate. You have two terms. But the F0, you have a minimum inside another minimum. So that's a difference. And this is something important. So here V is a non-Archimedean valuation, and the C is the same as above. You also have this simplicial area. And this depends on the Kähler form in general. This includes the singular analytic fibers. Okay, so the heuristic dense analytic subdomain Y, which we mentioned before, it has some explicit description, and will exactly satisfy this J of B equals F of this curly Y. Yeah, as pointed out, you should use curly Y here. Yeah, I'm sorry, this is a typo. You should use curly Y here, and then you can define F to be J inverse compose capital F and restrict on this curly Y. Okay, so at this moment, let's forget about all the mirror symmetry background, and we just look at this formula. Everything is explicit. So J, F, and this Y, everything is explicit and elementary. You don't need any flow theory to understand this formula. You don't need any like flow theory, category stuff. You just have some naive formulas, some elementary formulas. And more importantly, it has singular fibers. It can be defined over B, not just over B0. So I know this is not obvious at this moment, but you can see it will meet all the conditions for our definition of SYZ mirror. For example, you can match singular locus, you can match integral fine structure, and so on. Okay.
The point is just the disk that comes up in defining the transverse coordinate, but not S1 invariant coordinate, the Lagrangian fibration, right?
Yeah, I think this C is sort of related to the action coordinate. This C.
Right? It is the action.
Does it make sense? Okay, so let's move on.
Was I supposed to understand how you guessed this formula from the picture, or?
I don't know. So I can explain a little bit, but you just take a lot of trials. And so first of all, conservative Solomon has a prototype model for this kind of construction. It's very different, but I think morally the philosophy is the same. Conservative Solomon, so you just look at conservative Solomon's paper, you also have some this sort of construction.
I thought maybe you made some sense of what they wrote, which I understand, but I didn't understand.
So I can explain a little bit. So yeah, maybe I can. Yeah, maybe I can go back to this point later. So the motivation is sort of hard to explain. The idea is sort of from conservative Solomon, and you do a lot of trials and you try to modify it so that it can meet our purpose. So, and also you look at the previously, we have this identification between X0 check and the T plus and the union of T plus and T minus. So I mean, if you look at the conservative Solomon's construction, it also has some T1, T2, T3, and it has some embedding. And then I noticed that you just need to take a two chart and imitate their construction to finally find the following formulas. Okay, does it make sense?
It makes sense, but it just, you say something tantalizing with this disk, and I don't understand how your formulas come from this disk. But maybe I'll ask you later.
Okay, let's discuss this later. So a prototype of such construction is found by conservative Solomon many years ago. in a very different context. And controversial software uses 3 charts, but we only use 2 charts, which geometrically correspond to Clifford and the Chiganov tori. And we simplify it to 2 charts. And this is inspired by Gross-Hagenkiel or Gross-Siebert's work. And we see the formula of F is very elementary in itself, maybe still complicated, but it's elementary. And if we are content with the result without this duality, then there's nothing about flow theory. Okay, so I want to describe this image of J. So we can sort of visualize this. So you look at this formula, the important part is the first 2 coordinates. Q bar is just the first n-1 coordinate. And the picture looks like this. So you embed, so this is the dimension 2 case. So how do you understand this image? So in R2, we consider a broken line, in orange on the right-hand side, with a corner point at A. Okay, so this is something concrete. You just, you know, this is a broken line parameterized by this corner point. So you imagine this corner point can move, and you get a family. Now the image, yeah, maybe this can answer the question. So this image is simply the union of this broken line. So you can see this is your broken line, and you imagine this A is moving along this black curve, and you take union of all this broken line. This gives you the image of J. The black curve is the trace of the point and relies on omega in general. Also, you can look at the image of the singular locus. This is given by part of the corner point where Q bar is in the tropical hypersurface associated to this tropical polynomial. So if n is 2, then there is only one singular point, the blue point below. You have only one singular point. Yeah, maybe very surprisingly, you can show this tropical continuous map has exactly the same image. Yeah, maybe this can sort of explain why I need to define this formula. I just try a lot of times, and finally this match sort of precisely, and then you can define it. Okay, so also I can explain more about this definition. It's really found by hand, but let me try to explain the idea. The key observation is, so you look at this non-Archimedean valuation. Whenever this minimum is attained only once, then you have an equation, you have identity. However, if the minimum is attained twice, it may happen that this non-Archimedean valuation can be strictly larger than this minimum value. But this is ambiguous, which gives, so this, you don't know the precise value. You don't know the precise value. So if you want to define some map, this gives you some trouble, right? So in my opinion, so the motivation of this JF may be explained as follows. So this pair, J and capital F, is very carefully designed to eliminate this ambiguity. Yeah, I mean, it's really need some computation to understand what I'm saying here. The point is, like, you have this ambiguity, and you take these minimal values, you can kill this ambiguity. Yeah, remember, in our formula, you have a sort of minimal values, and you take this minimal value, then you don't have this ambiguity anymore. Yeah, that's maybe this is a good point to explain. And this ambiguity also plays a crucial role to create the singularity of the dual singular vibration. And regardless of how we find this pair from the family flow picture, it is really elementary to define them. and you can check a key lemma as follows. So you have a sort of a commutative diagram, looks like this. Okay, so which means this implies a T-duality condition. So you can identify this family flow dual vibration with the smooth part of this F. So the only place we need family flow is this is identification, as I mentioned before. And by this identification, we can also directly define this pi-0 check. And except this identification, like all this T plus minus, the gluing relation, the embedding J, the tropical continuous map F, the domain Y, F, G, can be defined directly in the pure non-Archimedean world. You don't need to worry about like moduli space of pseudo-holomorphic disk. Okay, any questions so far? Yeah, okay, let's move on. So let's look at this diagram again. So on the left-hand side, this follows family flow theory and the T-duality. So we put an analytic topology on this set, and the workhorse of Maslow's zero disk can imply an identification like this. And on the top horizontal arrow, this follows Gross-Hacking-Kier and the Gross-Siebert's program based on this identification. And on the right-hand side, this follows Conservative-Solomon. And we can further use this type 2 disk as information. Finally, you look at this mirror. It agrees with many previous works like this. Okay, so given the above discussion, our explicit T-duality picture is compatible with so many previous works. So it is very reasonable to believe these singular F fibers should be the correct dual singular fibers. And meanwhile, by the original family flow picture, we should expect these dual singular fibers are the Morgan set. However, unfortunately, the two approaches only have some partial agreement. The Morgan set is only a strict subset of the corresponding F fiber. Okay, so dual singular fiber is not a Morgan set. For simplicity, let's consider the case n is 2. So then the singular locus is only 1 point. So X is this, Y is this. So we have a pinch sphere Lagrangian. Yeah, just this one. Then the dual singular fiber. So remember, we have an explicit formula for our F. So you can explicitly find this dual singular fiber. Yeah, it's given by this. So we only focus on the set of closed point, for example. And here you can take some coordinate change. Here, C0 is precisely this symplectic area, but you can just do such a coordinate change, and this gives you a better picture. So yeah, maybe I need to speed up. So you can consider two different cases, 1 plus Y in lambda plus or not. And this gives you a decomposition of the dual singular fiber to S1 and S2. And yeah, you just find them explicitly. S1 is this, S2 is this. And more importantly, Hong, Kim, and Lau have already proved that the Morgan set for this singular Lagrangian is exactly given by S1. It's just S1. So we have nothing about S2. So this means the Morgan set is smaller. There are some extra points in S2 beyond the conventional Morgan picture. I don't know why. I'm also very curious about this, why we have such additional point. Anyway, one possibility is maybe we need some additional deformation data for Morgan set. Or you can, if you look at the non-Archimedean part, this analytic topology somehow more or less enforces us to handle the singular Lagrange fibers in sort of a different way. Yeah, but I don't know. I think we need further studies to understand this. And yeah, I don't know a good explanation why we have such an extra point. Okay, there are some further evidence for a folklore conjecture. So we know this conjecture due to controversial O'Rourke's and many others. The critical values of the mirror Landau-Ginzburg superpotential are the eigenvalues of quantum multiplication by the first Chern class. Yeah, so actually here we need some modification. So the grossest Lagrange vibration can be placed in not only X, but also possibly a larger ambient manifold. So for example, you can take CPN in this case. Often we can check the Maslov zero disk keep the same despite the ambient manifold. Then we will have the same analytic topology. So we can use the same analytic embedding and do a singular vibration. And on the other hand, there are no Maslov 2 disks in X, but there will be new Maslov 2 disks in this larger ambient manifold. So this gives you a superpotential on. Okay, be careful. This is only on the analytic open domain using this embedding. However, we can show this superpotential is polynomial for our example. And by our definition of SYZ mirror, the condition C, as I mentioned. So this analytic domain is Zariski dense in this algebraic variety. So you can extend this superpotential to the whole algebraic variety. And let's denote it by W. So in general, it depends on the Kähler form. And choosing different ambient space will produce different Landau-Ginzburg superpotential. Okay, so let's do some example. Yeah, we can, for example, take CPN. And the Landau-Ginzburg superpotential is defined by this formula. But it is not defined on some C star to the N or Cn. It's defined on this algebraic variety. It's defined on this algebraic variety. And you can also compute their critical point. And you can find them explicitly. These critical points are given by this formula. And you can also find the critical values. And you can check the folklore conjecture holds. So there may be many other examples if you consider other toric Calabi-Yau varieties, or you can consider other compactification. So for example, you can consider the product of two projective space. This is also compactification. Then your superpotential will look like this, defined on the same Y algebra variety. You can also find the critical values. So let's focus on a special case, N is 2 and M is 1. Then you can find the critical point. And using this dual singular vibration, you can find their base point is given by this formula. Here, A omega is some number, depends on the Kähler form. So it may happen that for some Kähler form, the number is 0. And if further, this two simplicity energy is the same, then this is a singular point. We don't know how to prove the folklore conjecture. But if they are different, this Q bar lies on the wall, and the conventional proof may fail because you have Maslov zero disk. But we can still prove it in another paper. So in general, we don't know if the critical points always avoid the walls or singular locus. Like for example, the walls may disperse in some open subset in the base. And for example, you look at blow up of CN along a hypersurface. So yeah, you need some new ideas to deal with this workhorseing for this folklore conjecture. Okay, finally, I want to describe some generalizations. So we can repeat our proof almost verbatim for more general examples. So like the previous, we use Cn and minus the divisor, but we can really take any toric Calabi-Yau manifold equipped with some toric Kähler form corresponding to some unbounded moment polytope defined by a set of inequalities like this. Here, VI's are the rays in the fan. Lambda I are some real numbers. And we may assume V1, Vn form a base, and the other rays take this form. Then the Calabi-Yau condition means there is some M0 such that the pairing of M0 and Vi is equal to 1. So in particular, we know this sum, right? This sum of coefficient is equal to 1. Yeah, this will be useful. And yeah, we can also define this XP. It depends on some moment polytope. It's very similar, and you also have some Gross's special Lagrangian fibration as before. On the other side, we define a low-rank polynomial. So the singular locus of the Lagrangian fibration is precisely decided by the tropicalization of this low-rank polynomial. Here, this delta I is some number in the maximal idea of the navical field, navical ring. It's sort of given by count of stable disk with sphere bubbles. Sometimes they are not zero, and the valuation in the smallest area of a sphere bubble. Finally, we define YH is given by this, is a similar formula. And the theorem says this YH is also SYZ mirror to XP. So you can just imitate all what I said before. You have this identification of family Floer space to some T plus, T minus with some gluing. And you can also define the analytic embedding G and the dual singular fibration F. Everything will be very similar. So for example, if you take this H to be this 1 plus Y1 plus dot dot plus Yn minus 1, then we go back to our previous example, right? And the corresponding tropical polynomial is exactly this minimal value. So which somehow plays a leading role in both A side and B side. For instance, it describes the walls on the A side. And it also appears in the formula of this F, also this pair J and the capital F on the B side. And this all gives the singular locus. Yeah, here I can explain sort of a version of SYZ converse. So the idea is that you can reconstruct the moment polytope from your low-rank polynomial or its tropicalization. So we can define a polytope by this inequality. And you can show this is isomorphic to the previous moment polytope. So this picture, unfortunately, will lost if you only work over C. So this is something really essential for the non-Archimedean field, I think. And I can take another example. Yes, so this is a general edge. So we can take a concrete edge like this. Then we can recover P. So we can find the corresponding rays in the fan. So how do you find it? Let me explain. So you see you have 6 monomials in this low-rank polynomial. And here you look at their power. This is 1, 0, this is 0, 1, this is 0, 0, this is 2, 0, 1, 1, 0, 2. So you look at the first 2 coordinate, 1, 0, 0, 1, 0, 0, 2, 0, 1, 1, 0, 2. They're the same. And moreover, you look at this form relation, we require the coefficient of all coordinate must have the sum equal to 1. So you need to put some other numbers to make the sum of this coordinate equal to 1. And you can also find these lambdas. You just look at the power of this t. So 0, -1, 3.14, 2, 0, 2. You get this lambda. So you have infinitely, you basically have infinitely many such examples. Yeah, and there are corresponding tropical hyperspace looks like this. So this is example 1. This is example 2. So you have many such examples. Okay, I think I can stop here. Thank you for your attention.
I still want to understand your formula.
Okay, yeah, I can explain this. You mean this formula, right? Oh, this is J and F.
Yeah. So what's going on here? I mean, isn't. So we have some does this disk live in the mirror, or don't we have a variety Y here? What is this disk? Where is the
so you can really think this F is like so you have two charts for this F, which is precisely this T plus and T minus.
No, so I'm not interested in guessing the formula. This I have no interest. Is there any way to connect this formula with this disk that you drew? Like, where is this disk living? Are you considering some kind of analytic disk inside the rigid analytic space or Berkowitz space?
Oh, analytification. Yeah. You need to take analytification.
What is like you're talking about some kind of area of this, but you're also inside an analytic space. I'm not sure, like fully confused.
Yeah, your audio is not so clear. Maybe you can say again. So
where does this disk live? What is that picture? That you have a picture of something, and is that a picture?
You mean this picture?
Yes.
Yeah. So this is the singular fiber in the Lagrange fibration. So this is another. Yeah. Maybe this is confusing. Yeah, I noticed that. So you know this. You know this O'Rourke's picture. You have a Lagrangian determined by some radius in the base and some another parameter. So it gives you a Lagrangian fibration, and this is just the singular Lagrangian. So
okay, so
it's really some vibration on the. I mean, yeah, I can draw something. Yeah, it's really some. You should really. This is a different picture, so you should really think like this. This is your singular torus, but this is not the same. I mean, you can consider this is a Lifshitz vibration. This is a Lifshitz vibration, and this is a Lagrangian vibration. You have two different vibrations.
Okay, I think I understand now. So you're using the fact that there is some Lagrangian vibration over B to write your formula here. So your formula is expressed the original Lagrangian vibration. Your formula for J.
Yeah. This, I mean, I draw this picture because this is something commonly used.
Considering Zoidman's version of writing this, there is no such thing, right? It's not actually such a complicated formula. You just take some maximum of 0 and valuation of x, maximum of 0 valuation of y, or something like that. There isn't really something that's complicated. There's just some taking valuations and taking maximum of 0, valuation.
Yeah.
Which is considered formula. But you have all these psi's here. So
psi. This simplified area like this.
Zoidman's formula doesn't have this psi.
Yeah, I don't know. I cannot find the precise formula with psi. I just know there exists some function. It's given by the simplified area. I don't know how to precisely find this PC.
But it doesn't recover Conservative-Zeugelmann's formula for n equals 2, does it? Does it recover?
I think in Conservative-Zeugelmann's construction, they don't have such function.
Yeah,
I think
does your construction equal to their construction, or are you giving something new? Like
it's not the same. It's not the same. It's different because so we really have some analytic open domain, right? But I think their construction is over the whole thing, and they don't have this per se. And
interesting.
yeah, I think. Okay. Yeah. Thanks.
Other questions from Zoom? Okay, well, let's thank Hang again.
Okay, thank you.